So today I'd like to start with some examples which are related to some of the problems that you were doing on the homework with the Fourier transforms. So first of all, this example will show that the Fourier transform of the function e to the minus pi x squared is just e to the minus pi s squared. So we could actually just call this t actually, let's do t squared. So we start with the time domain function. We take its Fourier transform and it gives us actually exactly back that same function but now in frequency domain. This is a result that is working with a function which is sometimes referred to as Gaussian. And you may, if you've done a little bit of probability theory, you might have recognized this function. This comes up in the probability distributions, which are called normal distribution. Okay, so in order to do this, we will need to use this fact, which we'll then prove at the end of this example after we do the Fourier transform. But the fact that we'll need to show is that the integral from minus infinity to infinity of e to the minus just x squared. Yeah, we'll just do x squared here in this one. E to the minus x squared dx is equal to square root of pi. Okay. From this, we also get, if I put u, just let's see, yeah. First of all, if I take the integral minus infinity to infinity of this function, then I get e to the minus pi x squared dx. We'll change it back to t in a minute, but just as a separate result, this particular integral, if I work with this one and I put u equal to square root of pi x, right? Then this is going to be the integral. I still go minus infinity to infinity. And in here I can just make the substitution of square root of pi x into here so that this is e to the minus u squared du. And then du is of course the square root of pi dx, right? So this dx should actually be 1 over the square root of pi du, right? So that comes out in front. And then I get the integral, right, is just computed by this answer here, square root of pi, and so this comes out to 1. Okay, so we'll use these facts in the working out this Fourier transform. So let's go to the Fourier transform now. So we'll take the Fourier transform. Well, first of all, we'll also give this function a name. Let's let f of t equal e to the minus pi t squared, right? Then we want to work out the Fourier transform of f of s. Okay, so that's going to be defined by this integral, minus infinity to infinity. And remember, just like on the homework here, we're not actually dealing with distributions, we're just dealing with functions, right? So when we do Fourier transforms, we're just working with the function definition. So I've got e to the minus pi t squared, and then e to the minus 2 pi I st dt. So there's our Fourier transform for the signal processing world 4, right? Then we'll do something else. We'll take the derivative with respect to s of this Fourier transform. Okay, so this is, again, right, Fourier transform of f of s, which is this whole formula here. So I can bring that derivative with respect to s onto this one term inside the integral, because everything else just depends on t, right? So I've got this integral e to the minus pi t squared, and then here, the derivative with respect to s of an exponential, I just get the constant in front of the s,
or the constant times s, which involves the t as well, times the same exponential, right? So that's the derivative, so I get minus 2 pi I t e to the minus 2 pi I st dt. Okay, and now we're going to do an integration by parts, right? Remember that the integral of u dv is equal to uv minus the integral of v du, right? That's our integration by parts formula. So let's just look at this. When you do integration by parts, you want to be able to integrate the dv to get v, and then you want to differentiate the u, right, to get du, so that all of these then are taken care of on the other side. So in this case, let's let u be e to the minus 2 pi I st, okay, and then dv will be given by these two parts here. Okay, so we'll take dv to be that, and then we'll go ahead and transform the integral up here. So let's say u is equal to e to the minus 2 pi I st, right, and then du, again, we're just taking du dt, because the integral here is with respect to t, right? So we've got minus 2 pi I s e to the minus 2 pi I st dt. And then we've got dv, right, was that whole thing. So that's e to the minus pi t squared, and then e to the minus 2 pi I st, and then finally the dt. Okay. So then what is v? So we're taking this now, v is just the integral of dv, right? So we're taking, it's the antiderivative of this entire expression here. So antiderivative of e to the minus pi t squared, e to the minus 2 pi I st dt. I missed this one, sorry. I should have also the minus 2 pi I t there. Right, that comes in there. Oh, that's the part, yeah. I was just gluing the wrong pieces together. So it's this, and then minus 2 pi I t, and then dt. Yeah, that's good. Okay, so then this part is just minus 2 pi I t and dt. Okay. All right, so for the antiderivative of this, right, if we take derivative of something like e to the minus pi t squared, right, what is that? Well, that's just going to be minus, I take the derivative of the inside, right, this exponent, so it's minus 2 pi t times e to the minus pi t squared. And we pretty much have it right there, right? So in other words, when I take the derivative of this function, I get this. The only thing is exactly I need an I. So if I take derivative of I times this, I get this, right? And that means that this entire antiderivative is just equal to I e to the minus pi t squared. So that's our v. Okay, so going back then to this integral, right? We were working here with the integral, which is the derivative of the Fourier transform, is this integral, and now we've transformed it into u and dv, and now we can use the integration by parts to write the answer. So this is going to be, we're going to go back to using integrals, or sorry, limits as well, minus infinity to infinity on everything, right? So first of all, we've got uv, right? So that's e to the minus 2 pi I st, that's my u, and the v is there, e to the, or I e to the minus pi t squared, That's going minus infinity to infinity. I'm going to go minus the integral of v, integral minus infinity to infinity. This is my v, I e to the minus pi t squared, and then v, and then du, which is all of that stuff. So minus 2 pi I s e to the minus 2 pi I s t dt. All right. Okay, so what do we have here? So first of all, here we've got integral minus infinity to infinity on the t value, right? And we've got minus a constant times t, and then minus another constant times t squared. Both of those are going off to infinity in some way, right? Or actually, sorry, off the t squared and the t are going off to infinity. But when I have a minus t going to infinity, of course, that's going to 0. The only case where something is going to plus infinity, right, this minus takes care of these both going to infinity, and I have a minus, so this is going to 0. In this case, if I put t going to minus infinity, this would be going to plus infinity, all right? But the fact that I've got two exponentials here, the one with the t squared is approaching 0 faster than the one here going to infinity. And so, in fact, this is just going to be 0, all right? And then finally, in the last case, right, we get minus, so this whole thing is just minus this integral. So let me factor out let's look at a few things here. I've got an I here. Let me just make sure I have enough yeah, I've got actually two i's. I've got an I here and an I here. That's a minus 1, another minus there. So those minus I squared is just equal to 1, right? So we're going to cancel those parts. So then I'm going to pull out a 2 pi, right? So I'm going to get a minus 2 pi here. And then what do I have left over? Let's just write that one down. So I've got minus infinity to infinity with the minus and the 2 pi out in front. And then I've got e to the minus pi t squared. And then I've got, oh, yeah, the s. I can also pull the s out, right? Because that does not, this integral is with respect to t, right? I can't pull that s out, but I can certainly pull this s out, okay? So I've got minus 2 pi s, and then I've got this function, and now all this stuff is gone, and I've got e to the minus 2 pi I s t dt, okay? This, of course, this entire expression is just the Fourier transform of this function here, right? Which is what we started with. So this is minus 2 pi s times the Fourier transform of our function, right, that we call f of t, is just sitting there. So that's Fourier transform of f now as a function of s. Right, so this tells us that when I take the derivative of the Fourier transform, I get this minus 2 pi s times the Fourier transform. So what kinds of functions have this property? So what kinds of functions, let's call them g, have the property as follows, and that is if I take g prime of s, right, that's our derivative, it's equal to minus 2 pi s times g of s. Well, you can probably think already that, well, isn't it this kind of function actually? This kind of function that we're calling f here, if I look at it, if I take the derivative, I get 2 pi t, right? Or if I write this as a function of s, I'm going to get minus 2 pi s. So in fact, g of s equals e to the minus pi s squared is certainly 1, right? if I take the derivative of this, I get minus 2 pi sg of s, right? The only other thing that we need to check here is that it might be a constant times this type of function, right? So if we're going to get then the Fourier transform of f of s is going to be some constant times e to the minus pi s squared. And what is that constant here? It's the Fourier transform of f evaluated at 0, because if I put a 0 in here, I'm just going to get the constant. This will turn into 1. I'll just get the constant in front. So this is in fact the Fourier transform of s at 0. Okay. And finally, if I can just squeeze that part in here, the Fourier transform of f at 0 is just in fact that integral, right, that we did before. So this is minus infinity to infinity e to the minus pi t squared dt, right? That's our Fourier transform of f. We just plug that in when s is equal to 0, right? This is exactly the one we did before, and this integral is 1, right? Which is the one we quoted before. Sorry, we didn't do that integral yet. We just gave this quote at the beginning that when you do this integral, you get 1. And so that means that this constant is 1. So that means finally that this Fourier transform is indeed just e to the minus pi s squared.